Hi, welcome to this video series on cryptography. Today I'm going to talk about some very basic math constructions that we need for cryptanalysis as well as for constructing cryptographic protocols. Oftentimes we need to compute GCD between two numbers. We also need to compute extended Euclidean algorithm. So for that, we need to have a good understanding of how GCD actually works. GCD is a really old idea. I could trace it back to Euclid's work. Euclid is arguably the one who published some interesting algorithms related to Euclid, GCD algorithm. So I'll start explaining intuitive idea first, and then I will explain the programming algorithm that we could easily codify. First of all, GCD stands for greatest common divisor. So given two numbers A and B, they both cannot be zero, okay? Otherwise it's not defined. One can be zero, that's perfectly fine, but both cannot be zero. So what is GCD function saying? GCD function is saying it will find a number D, okay, with certain properties. What are the properties? The number D is, of course, an integer number, okay? D has to be a number greater than zero, right? That's the largest part, and it has to divide both A and B, okay? So these are the conditions. It has to divide both A and B, okay? And there may be other divisors of A and B, right? Suppose, let's say C is another divisor that divides A and divides B, okay? What can we say about C? C better be smaller than D. Okay, that's the purpose of the greatest common divisor. That is the largest number that will divide both A and B. Okay, that's basically the definition of GCD. For example, what is the GCD of say 8 and 12? Okay, it cannot be more than 8 because 8 is the smaller of those two. So we can immediately tell, hopefully immediately tell, GCD of 8 and 12 is 4, okay, because 4 divides 8, 4 also divides 12. 2 also divides 8 and 2 also divides 12, but 2 is smaller than 4. So you pick the largest number that divides both 8 and 12, okay? One possibility for small numbers is just write the divisors of 8, divisors of 12, and then pick the largest numbers, right? For example, the divisor of 8 is 1, 2, 4. Of course, 8 also divides 8. And then for 12, it is 1, 2, and 3, 4, and 6. Okay. As you can see, the number 4 is the largest number that is common across both of these divisors for 8. These are the divisors of 8, right? Curly bracket. I tried curly bracket, but anyway, divisors of 8. These are divisors of 12. And you can see 4 is the largest number that divides both. Okay, that's basically the definition of GCD. So I actually looked into Euclid's book, Elements book, and the way he introduced GCD is pretty interesting. So he has one scale, right? Let's say the scale length is here 12, and then you have another scale, say of length, say 8. Okay. So the question now is, what is the largest scale that can measure both these scales? Okay, so the answer turned out to be 4, as we saw in the previous demo. So how do we get to know the number 4 easily, given two scales? So his idea is this. His idea is that don't care about the parts that 8 will exactly measure. Okay, so maybe 8 will measure exactly up to this part, right? So what is left is this part. So find the largest scale that can measure this part and this whole scale. Okay, that's basically what his idea is. So what is the leftover of the largest scale and then the smallest scale? So I will prove mathematically why that is correct in a moment, but let's just reason about it. His idea is like this. Suppose you have a scale, let's call this as A equal to 12 scale and B equal to 8 scale. So what we are going to do is, instead of computing GCD of A comma B, is saying compute GCD of B comma R. Okay, what is R? R is the remainder of dividing A by B, okay, which means like this, right? Remainder of A divided by B is a number between 0 and B minus 1. So the number R is going to be from 0 all the way to B minus 1. And B is, of course, greater than R because R is a remainder. Therefore, we can keep on calling GCD recursively to get the answer. Okay. So this is important not to confuse you. Okay. So this is the GCD algorithm. Now I will show you the math behind this equation. Why is this working? Okay. So the idea is pretty neat. There's a nice division algorithm in number theory which says like this. If you are given a number A, it doesn't matter whether it's greater than 0 or less than 0, it's an integer. There exists other numbers Q, and we can write it like this. Given a number A and B, you can find Q and R such that A equal to QB plus R, where R is bounded by, what is it, R bounded by? R cannot be more than B, okay? It's strictly less than B, in fact. This must be clear when we did the division algorithms, right? When A is divided by B, you get a quotient, and then quotient times B plus R should give you A. This is the basic division rule, but it's nice to see it algebraically. Okay, so this property is well known. It's called division algorithm. Given A and B, it will help you. Actually, there is no real algorithm from the division algorithm, but you can find a Q and R which satisfies this property given A and B. I mentioned earlier that computing GCD of A comma B, right, is same as computing GCD of B comma R. Now we need to convince ourselves that's the case. Why is this working? The reason why it is working is simple. So let's take this. Let's take the case that A and B are both not 0. Okay, either one of them can be 0. That's not a problem, but both cannot be 0. If A equal to 0, B equal to 0, then you know for sure R is 0. Otherwise, this equation won't hold right. Therefore, when R is 0, when well, this is simple now. When R is 0, B is 0. You don't have to worry about it because we can imagine GCD of 0, 0 is 0. And this is also 0, 0. So both of them are the same, right? For a moment, GCD of 0, 0 is same as GCD of 0, 0. Okay, so that's true. Let's consider the case when both of them are not 0. And that's where the interesting little bit of complexity comes. So what do we know when we say GCD of A comma B? We know there exists a number D which divides both A and B. That means D divides A and D divides B. Okay, there is another interesting theorem that tells us that if you have a number D that divides A and divides B, it means the number D must divide A minus QB. This is number theory proposition that I'm using without proving it. It's coming directly from the definition of division. Okay, so if a number A is being divided by D and B is divided by D, then A minus QB will be divided by D. That means this is true. Okay, which means what is A minus QB? A minus QB is R from this equation, which means D divides R. Okay, so what we learned is that given GCD of A and B, which is D, right? Let's assume D is the GCD of A and B. We learned that now D divides R also. Okay, so now look at the right hand side. Okay, right hand side says GCD of B comma R, right? We also have a nice property here now. D is dividing R. We also learned D is dividing B. Okay. Only thing left to prove is that there doesn't exist a number greater than D that will divide both B and R. That's the only thing we need to prove. So let's assume there exists a number C, which is GCD of B and R. Okay. What does it mean? It means C divides B and C divides R. Okay. What does that tell us? That tells us that because of the division property, that this number C must be dividing Q times B plus R. Okay, this is the basic rule of math division. Given this constraint now, okay, what is QB plus R? QB plus R is nothing but A, which means the number C divides A. Okay, so what did we achieve so far? We achieved that we found a number C which divides A, C also divides B, Okay, what it means is that we can now compare that C with D, but D itself is as a GCD of A and B. Therefore, C must be smaller than or equal to D, right? This comes straight from the property of definition of GCD, right? Because that we know that D is a GCD of A and B. That's what we assumed. And we are asking, can there be a number other than D that divides B and R? If it exists, what can we say about the relationship with number D? Okay, so we assume D, there exists a number C which divides B and R. We concluded that that number will divide QB plus R, which means that number will divide A, because A is nothing but QB plus R. So the fact that the number C divides A and C divides B tells us that C must be less than or equal to D, otherwise say D cannot be the GCD of A and B. Okay, therefore this property is true. Okay, so we can now have a simple algorithm that will recursively call GCD until our R becomes 0. Okay, when R becomes 0, we know for sure what is the answer, right? We can immediately tell the other number is the GCD, because I will tell you this because it's not necessarily so clear. What is the GCD of, say, A comma 0? GCD of A comma 0 is actually A. Okay, A is the largest number that divides both A, of course, A divides A, and A divides 0. Okay, because you can write 0 equal to some 0 times A, for example. So A divides A and A divides 0. So this is important to remember. Okay, this is important to remember. So now let me show you my recursive implementation. Of course, there are non-recursive implementations also available. I will share that with you. So I will show you now my implementation of GCD. That's basically what I'm going to do. So what you're seeing here is a little program that I will just zoom in a little bit. There are other things that I will talk about later, but at this point, I'm going to just focus on the GCD part, right? I'll come back to extended GCD in my next segment. So what is this program doing? It's basically checking whether B is 0, right? If B is 0, it returns A. Otherwise, it returns GCD of B and R. What is R? R is A mod B. Okay, that's basically what I have shown on my whiteboard. Okay, so this is the little piece of code. Now we can actually run this within Python import okay, from xgcd import star. Okay, so I'm going to print GCD of say 2 comma 0. We expect the answer to be 2. What about GCD of 2 comma 1? We expect the answer to be 1. We can try GCD of 8 and 12, which must be 4. Okay, we can try GCD of 6 and 12, which must be 6. It must be the same as 12 comma 6 as well. So it works. Okay. The reason it works is, as I proved in my whiteboard, that it uses the properties of division to recursively reduce the size of the remainder to explore until the remainder becomes 0 and then stops. So let me quickly recall this algorithm, right? What is that we are doing? This is the portion of the algorithm of interest. If one number is 0, the other number A becomes the GCD. Okay. Let's focus on this a little bit. What happens if A is smaller than B? If A is smaller than B, it comes here to the return part. B is basically a large number, right? What about A mod B? Remember, A mod B is something less than B. That means let's say, for example, more concretely, A equal to, say, A equal to 8 and B equal to, or take like this, A equal to 5 and B equal to 6. Okay, so GCD will be 1. So what happens now? At this point, our B is 6, right? So we are computing GCD of 6. At this point, what we are computing will be GCD of 6, comma A mod B. Remember, A is smaller than B in this case. That means it will be GCD of 6, comma 5. Now it swapped the A and B. Now next time it will be computing GCD of 6, comma 5, which means it will come here and then it will go to find GCD of 5, comma 1. And because next time it will come and it will compute 1, 0, and at this point it knows GCD is 1. Okay, that's basically it. So I will clean this thing. Okay, so this is a simple algorithm, but sometimes it can be confusing, but it's one of the very powerful algorithms. It takes time to get through this idea, of course, but the most important property we are using is this, right? To be able to model our equations in a simple way, like A equal to QB plus R. This is the foundation. That's the reason why we are able to compute GCD of A comma B is nothing but GCD of B comma R. Okay, that's exactly what we did. In our code, we didn't use R, we used B comma A mod B, right? A mod B is R, where R is nothing but A mod B, right? Okay, so that's basically it for this part of the segment. Next segment, I will explain how we can leverage the Euclidean algorithm and extend it to extended Euclidean algorithm. Okay, thank you.